We have already learned that a field acts on certain, let's say, bodies with certain properties in a way that can be demonstrated with the gravitational field. So a mass causes a gravitational field, and if there is another mass within this gravitational field, the field supplies that second mass with gravitational, or what we call gravitational potential energy. And in the electric field, it is quite similar, with the only difference, or not the only, but with one major difference, that the field is caused by electrical charge. Now, when another charge is located in this electrical field, it gets electrical potential energy by that field. Now we need to distinguish between a few different cases. First of all, if, for example, we have a huge charge that is creating the field, and then we have a comparatively small charge that we call sample charge. Now we know that each charge is creating an electrical field, and that there is an interaction between these two fields. And from gravitation we know that the force between two masses is equally and oppositely directed. So both act with the same force on each other. It's the same here, but if the masses, or the charges in our case, are so different in their size, then we can neglect the force that is caused by the smaller charge or mass in the other case. So that's when we say, okay, that we only look at the greater charge, the bigger charge, and calculate the force that the field of that bigger charge is acting on that sample charge. The other thing that is important is, now when we look at the electrical field, a charge can never exist without a mass. So that means that normally also, or always, gravitation is involved. But in S5 we have already learned that the electromagnetic interaction or force is a lot stronger than gravitation. So normally, if it is not explicitly mentioned, we neglect the gravitation in the topic that we are dealing with now, electrical fields. There's just one situation that I can just recall, and this is the Millikan experiment, where we need the gravitation in particular, otherwise it won't work. But in most other cases, as I said, if it's not explicitly mentioned, we consider the gravitation as being so small compared to the electric force that we neglected. So now it is a bit more difficult in the electric field, because in the gravitational field we have the mass, and this creates a gravitational field. But normally in nature we don't have any charged particles, so the charge has to come from somewhere else. As we have learned before, we can generate charges by friction. Another possibility is a voltage. A voltage is a potential difference, and this is always followed by some kind of charge. So in a battery, for example, with a certain voltage, there are two, the plus and the minus pole, meaning that we have some more positive charges on the one side and some more negative on the other side. And as we've already learned before, the amount of charges on both sides has to be the same. It's just a different sign. So the voltage can be considered as a reason for a charge, and this usually causes an electric field. So what we want to do now is look a bit closer at the relationship between the voltage and the field strength, as we haven't got any formal relationship between these two quantities. Now, in order to do that, we need to go a bit back in our topic to mechanics and what we've done there before. So we start with the definition of work, and the work is defined as the force that acts along a certain way or distance, which we call S sometimes. It's called D. I suppose it's because of the German word Strecke. So if I make a quick drawing, so since we are in mechanics, this is the gravitational homogeneous field. We have a certain mass in here, and work is only done if the mass is moved parallel or anti-parallel to the force vectors. Meaning that if we carry a mass perpendicular to the force vectors, that means work is zero. Why is that? Because we have the dot product of two vectors, and if the angle is 90 degrees, we have the cosine of 90, and this is zero. So sometimes it's called something like the effective force, because along this no force is acting. This sounds a bit strange because the force is still pulling the mass down, but no work needs to be done to hold that mass on a certain height. Yeah. So to move it in a 90 degrees angle, no work needs to be done, because we are not moving the object against a certain force. Yeah, of course there might be friction, for example, but in a vacuum with a small mass and so on, there is no work necessary. Just to mention a special case where we need actually the dot product would be, for example, if we move it in a certain angle. Then we need the cosine or the dot product to calculate the amount, which is this one here. So then the it splits up into two different parts, one in x direction, which is where the work is 0, and one in y direction, where the effective work is being taken into account, which is this one here. Okay, but that's something. Well, that could be in an analysis question in a test, for example, but it won't bother us in further on in the mission. Okay, so as I said before, normally we can, as indicated here, just use the normal product because the force and the distance point in the same direction or opposite direction. We also know that in a gravitational field, the force is mass times acceleration. By the way, here the same acceleration is a vector, or it's not the same, but it's a scalar product, I think. What's it called? Yeah. Normal product, yeah, scalar with a vector. Whatever that means, that force is a vector. It's different. Work is not a vector. So work has no direction. It only has a sign. And the sign of the work or the energy can be interpreted as energy is going, or the body or the object gains energy, then it's plus, or it loses energy, then it's minus. Further on, it will be important to draw a connection between work and energy. So as we know from S5, when energy is converted into a different form of energy, for example, potential energy is converted into kinetic energy, we need work. And in that case, it's, for example, acceleration work. Since that energy and this one here are equal in their value, we can consider that also the work that is done is the same. Okay, so we have an equation where potential energy equals the work that is done to transform that energy into kinetic energy, which is again the same. So work has, if we look at it, work has the same units, and so therefore it must have the same value as the energy in that case where it's converted. So if we put this force into that formula, then we have m times g times s, and in the gravitational field, the s in the direction of the force would be the height. Okay, so if we move a mass upwards or if it's falling down, then we can call it the distance is equal to the height. Strictly speaking, we need to say delta H, because the height is hard to define. Okay, so if we have a table, for example, that has a certain height, let's say 1 meter, but the table might be located on the first floor of a house. So what's the height of the table now? This might be 3 meters. And again, the house might be located on a hill. And the hill might have a height of 200 meters. And then again, sea level is somewhere here. Okay. So it's as long as we work with a homogeneous gravitational field, it doesn't really matter, because the force is linear. So that means the force. Here we go. The force is the same, no matter if it's here or there, because the field strength is constant. So the G is the same everywhere in that field. So that is why we can just set, for example, the floor here as here is the potential energy is 0, and then we have a delta H. So because if we say a height of 1 meter, the next person will say, okay, where is 1 meter? From sea level, 1 meter. So, but if we say delta H, it doesn't matter where we are in that field. It's just we move a mass along with the force, or in the direction of the force vectors, a distance of 1 meter. So now, then again, why do we have to write delta E pot? Because we know that the potential energy is 0 just somewhere in infinity, in reality, in the radiational gravitational field. So what we do here is the body has a certain potential energy here and a certain potential energy here. But since we say, okay, here we set the height as being 0, and here height is 1 meter, then we have a difference in the potential energy, because work needs to be done. And as I've explained before, we can say the energy is equal to the work that needs to be done to move a mass in a field with a field strength of G over a distance delta H in direction of the field vectors. Okay, now this looks a bit messy, so I clean that up. And now we turn back to the electric field. And what we have already learned is that the field strength is force divided by mass. Now, what does that actually mean, or why do we say that? So again, looking at the gravitational field, we say F is equal to m times G. So G must be F by M. And that was originally the definition of the field strength. Because we said, okay, here is a mass. Oh, let's write a capital letter. So a big mass like the Earth or the Sun, generating a gravitational field. But we don't see that field as long as there is no other mass inside that field. And only now a force is acting. Without that second mass, there is no force acting. So we could ask the question, is the field actually there or not? But since the field is only a theoretical model anyway, you could argue the field doesn't exist even if there is a second mass. Yeah, just by the way, Einstein explained this in a completely different way, where the space is bent around a mass, and that's why the masses are falling down, because of a curved space. But this is a different topic. Anyway, we're working with the field, and we know that so only now we can investigate the field, because the field is something we can't see, we can't really measure. But with that second mass, we can observe the force between these two masses. There is an attracting force. But then again, that mass creates another field, and actually it is the interaction between the two fields that causes the force, or that concludes in that force between them. So it's rather difficult to, well, then the force, as we know, depends on the mass, the small mass that's inside. So if we have another small mass, but it might be twice as big as the other, the red one here, so the force is a different one. It's twice as much as the first one that I've drawn. So it is not possible to describe the field of this big mass, of the planet, for example, without the second mass. So in order to have a quantity that describes the gravitational field around that mass independently from any other object, that's why we say we need to divide the mass, the force that we can measure by its mass. So we have something like force per kilogram. And this is independent from the mass itself, because it cancels out of that formula. So even if we put in here the formula for, or the term for the radiational field, the Newton's law, the small mass cancels out, and what we have is something like the force that acts on it. It is the same as we put in here 1 kilogram, because if this has the value 1, then what is left is just this G times 1. So it is kind of force per kilogram. Now, here in the electrical field, we define the field strength in exactly the same way. So our E is what we had before with the G. We say we can measure the force, but only if there is a second charge in that field. So I could just come here and replace the m's by q. Say, oh, here we have a large charge, which doesn't mean that it has to be a large body. It can be a very small body, but highly charged. And then we've got some smaller masses, some smaller charges. And again, the same problem. The force depends on this, the amount of this small q. So in order to make the two charges or the field independent of that second charge, we divide it by the small q, and again we have something like the electrical force per coulomb or per charge, let's say, yeah, unit of charge. And so now we can describe the electrical field that is generated around a charge independently from any other charge. And we can manipulate the formula, and then we get an expression for the force itself. Now, of course, there is the small q here again, because it is, if we talk about force, that can only be between two charges. There can't be a force of one charge. So that makes perfectly sense here to have this q in that formula here. And now we look at this situation where we have a small charged, positively charged particle and a homogeneous electrical field that is created by a potential difference U, and the plates have a certain distance d. So we know that work is equal to F times S, and in that case we want to move that little positive charge, let's say from the top to the bottom of this. So the work is F, and that is indeed what we do now, is we can calculate the energy that is stored in this electrical field. So that's when we insert the distance d. Now when we do that, and for F is Q times E, then we obtain the work in this electrical field that needs to be done to move a charge small q in a field with a strength E along the distance d. And this is the work that needs to be done, but also the energy that is being converted. Okay, so it's easier to look at the other case where the positive particle is moving from here to there. So if we release that particle here and it's moving all the way here, then the electrical energy that is given to the charge is converted into kinetic energy. It accelerates, and so that electrical energy is Q times E times D. Now, this is important. We could write, take that away for a moment, E is equal But what happens here is, oh, we've got two E's. One for the energy, one for the electrical field, but we usually don't write the vector, because otherwise we would have to write this as a vector. Since we only mostly look at the cases where the direction is the same, we don't need the angle or anything, the dot product. So we want to make it as simple as possible, leave the arrows away. Now we would have a problem. So instead of using the E, we keep the W for work and say, oh, we know that work and energy have the same value, so this is electrical energy, or the work that needs to be done if we move it into the opposite direction, or if we say this is acceleration work. So look at what our intention was. We want to investigate a relationship between the voltage and the field strength. Now, we've got the field strength in our formula, and we've got some kind of energy on the other side. So how do we get in the voltage here? What we've learned before was that the potential, or that the voltage is the energy per charge. So when we look at, let me just explain this once more. We look at a battery, and if there was here some positive atoms with negative electrons around it, these electrons have no kind of electrical or potential electrical energy, because they wouldn't move anywhere else. Indeed, there is an attraction, but that's just within the atom. Okay, so since there is no charge at all that is being separated, there wouldn't be any potential difference. There's no voltage. So if we connect this with an electric circuit, nothing happens. So what we do first is we need to separate the charges. So, or some more negative on that side and some more positive on this side, for example. And what happens now? These ions, or the separated charges, they want to combine. So there is an electric field between these separated charges, or an attracting force. So the but here is something like a border, a wall that it can't get through. But if we connect these two poles, then the force can act, and the electrons move from the negative to the positive side. Now we know that there are different voltages. So what we've said is, if we want to say what does voltage mean? It means that we can give the electrons more or less energy. And I'm not sure if you've done that, but I have a certain model that I like to use, is again to compare it with gravitation. So the electrons are like little balls, and if they are located on the ground level, they have zero voltage because they wouldn't do anything. Okay, they just lie on the ground. But if we have an elevator here that brings the electrons on a certain height, then the balls would have potential energy, And according to that, the electrons have electrical energy. That's what happens in the battery. And the higher we put them, meaning the more work we have done on them before, the more potential energy or electrical energy they have. Still, nothing happens. But connecting that to an electrical circuit means that, for example, I put a slide here and it's going back to ground level. We know the higher the slide is, the faster the electrons will be when they reach the ground, meaning there's more energy. They can, well, for example, leave in this resistance, or if we put a lamp here, then the energy is given to that lamp. So on its way, we can have, so for example, this is a water slide, so they're coming down really fast without any friction or losing energy. But if we put, for example, a piece of grass here, then they would slow down, giving energy to that, that bit here, and then they come here, they come back here with a slower speed. And it's just a model in an electrical circuit. When they reach the positive side, they have indeed, there's no energy left. So they give away all their energy on their way, and that means if there is no resistance or anything at all in the circuit, then I don't know the English word. German is Kurzschluss, but you know what happens then. So that's our definition, energy per charge. So how much each coulomb or how much energy we give it. And then we see that we have the here the energy, so it's U times Q, and from above we have seen that Q times E times D, and that cancels out, so E is U divided by D. So it's voltage per distance in such a conductor that we have here. So the higher the voltage that we put on this conductor here, the higher the electrical field, and with it the energy that's stored inside it. And the greater the distance, the smaller the field strength, okay? Because it's anti-proportional. So what we want to try in order to store as much energy as possible is to keep the distance as small as possible, but we can't go too much towards the other plate, because then if we have a medium here like air, it can happen that the charges just jump to the other side, like small flashes or something. So that's why, but that would be later. We can put something between the plates, and we will learn that it even increases the electrical field. Now at last, just it's a very small look at the unit. So it's U divided by D. So it's volt per meter. It can be converted because volt is not a standard unit, so we can convert this into standard units and get something else. But that's rather complicated and not necessary at this stage.